circumstances, there are 5 marks which are reserved for the attendance. Okay. Now, we don't know what will happen this semester because of COVID, but we are going to keep our record, complete record, so that we are in a position to take a call as per the instructions which we received from the University of Delhi. Okay. That is why I am maintaining my complete attendance record. So please do remember to mark your attendance every time. Okay.
Yes, ma'am.
In the last class, we had discussed about the half adder and the full adder. Do you have a problem in these topics?
No, ma'am.
Okay. So today we are going to look at the half subtractor and the full subtractor. So generally I give these to the students as assignments sometimes, but I thought I'll discuss it with you since we are not in an offline scenario. So I thought I'll discuss the half subtractor and full subtractor with you too. Okay, so this is going to be our discussion today. The topic of our discussion today. We are going to first design a half subtractor and then the full subtractor. Okay. So what is a half subtractor? Like a half adder, a half subtractor subtracts only 2 bits of information. Okay, it deals with only 2 bits of information. The term minuend is a Latin word implying a quantity or number from which the another quantity is to be subtracted. And the number which is to be subtracted from the minuend is called the subtrahend. What is it called? It is called the
Subtrahend.
Yeah. So if I'm doing x minus y, it means that x is called the minuend and y is called the subtrahend. Okay. So we are going to be dealing with a subtractor which does what? Which does x minus y, where x and y both are Boolean variables. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right.
Yes, ma'am.
So just give me a second. Can you see this diagram?
No, ma'am.
No, ma'am.
What happened to it? But you can see the screen, right?
Yes, ma'am.
Yes, ma'am.
Okay, just give me a minute. Huh? Yeah. Let me know when my screen is visible to you. Is it visible?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right. Okay. Right. Yeah. Who will read for me
Ma'am,
today?
Mayali.
Ma'am, Nandini
Okay,
Vashisht.
okay.
Who is this? Sorry, come again.
Nandini
Nandini
Vashisht.
Vashisht. Yeah.
Okay, ma'am.
Yeah. Thank you, Nandini.
Ma'am,
Please
you're
read.
welcome.
Given the two input bits whose difference is to be calculated, namely the manuend and the
Read from the
subtrahend.
read from here. Read from here. This is the
From where?
definition of a half subtractor.
I'm sorry, from where?
The earlier paragraph. The combinational circuit used to perform the binary subtraction
Okay,
of
okay,
two or
sorry,
more
ma'am.
binary numbers.
Yes, okay, got it. The combinational circuit used to perform binary subtraction of two or more binary numbers is called a subtractor. A half subtractor is used to perform subtraction of two bits, given the two input bits whose difference is to be calculated, namely the manuend and the subtrahend. The objective of a half subtractor is to generate two outputs, namely their difference and borrow. The term minuend is a Latin word implying a quantity or number, a number that is to be subtracted from the minuend. And here's the diagram. The subtraction of two binary bits is
So this,
illustrated in the
what you
figure.
see here is the block diagram of the half subtractor. So as was the case in the half adder, we have two inputs here. The inputs in the case of a half subtractor are known as the minuend and the subtrahend, as I just told you. And we are going to be having two outputs in this case as well. Obviously, the first one would be the difference of x and y, and the second one would indicate whether or not we require to take a borrow from the next position. Okay, so if I require to take a borrow from the next position to do this calculation, to do this subtraction, then we will put a 1 in this column. Okay, so these are the two outputs that are generated for each value, for each input combination of the variables x and y. Is this clear?
Yes, ma'am.
Yes,
So
ma'am.
this marks the first step of our design process. That is, we have laid down the block diagram. Yes, Nandini.
Only in case second, where we need to subtract 1 from 0, do we need to borrow a 1, which makes the minuend 10, 0. The resultant subtraction of 1, 0 minus 1 then produces the difference 1.
So this I'll just explain to you. The next step would be to list the truth table. But before that, let us first see how binary subtraction is done. Okay, let me just update you on how binary subtraction is done. So there can be four cases, you know that. We may have 0, 0, 0, 1, 1, 0 and 1, 1 as the four input combinations to our variables x and y. And let us see what happens each time we try to subtract y from x. Okay, so 0 minus 0 means I get a difference of 0. Yes or no? 0 minus 0 is 0. And
Yes,
did I
ma'am.
have to
Yes,
borrow
ma'am.
anything?
No, ma'am.
No,
No,
ma'am.
ma'am.
Next, let us see 0 minus 1. Okay, so as you can see that I cannot, subtract a 1 from a 0. So what will I have to do? As in our normal subtraction, we will borrow a 1 from the next significant position, right? Yes or no?
Yes,
Yes,
ma'am.
Yes, ma'am. Yes, ma'am.
Which will make this as 1 0, right?
Yes,
yes,
ma'am.
1
Yes,
0 means 2 in decimal,
yes,
right?
ma'am.
yes.
Yes, ma'am.
So, so when I subtract 1 from 2, what do I get?
1.
1.
One.
So in this case, please note that the difference is 1 and we also had to get a borrow from the next stage. Is there any problem?
No, ma'am.
Right? Let us see this in the truth table. So This is the first case that we had just seen where the difference in borrow were both 0. And this is the second case that we are discussing. So 0 minus 1, we take a borrow and then the difference that we get is also 1. Any problem up till now?
No, ma'am.
No, ma'am.
Let us look at the third case now, which is 1 minus 0. So the difference is 1, clear enough, and we did not have to borrow anything, right? Any
Yes,
problem?
ma'am. No, ma'am.
You can also see this as the reflected as the third row in the truth table, right?
Yes, ma'am.
Now the fourth case is again very straightforward. So 1 minus 1 gives us a 0
0.
and we did not have to borrow anything again, right? So both the difference and the borrow are 0. Any problem?
No, ma'am.
No, ma'am.
Right. Okay. So I request you now to do the next steps on your paper. So you have a notebook with you?
Yes, ma'am.
What is the next
Yes,
step?
ma'am.
What is the next step in the design process?
Deriving a Boolean expression.
Yes. We need to derive a Boolean expression for both the difference and the borrow. So I request you to please try it out yourself.
Okay, ma'am.
Ma'am, the difference is X XOR Y.
Okay. Let's see what other people get.
Yes, ma'am. The difference is x dash y plus xy.
And what is borrow?
X dash y.
Okay. Let us see who can confirm this. Amita Singh.
Yeah, ma'am. Borrow is X dash Y.
Okay.
Yes,
Amita
ma'am.
Singh.
Borrow is Excel.
Asta Bishnoi, yes. Tell me again.
Ma'am, the borrow is Excel by.
Okay. Aromo. Hello, beta. Are you there? Aromo. Kirti Mondal. Lakshika. Am I audible?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Where are these people? Why are they not responding? Lynette? Okay, that's okay, Kirti. Are you following what we are doing in the class? Lynette, are you there? No. Mishika, the borrow is x dash y. Right, students?
Yes, ma'am. It's
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes. Ching, how are you? Are you there, Ching? I think we need to make it a more interactive. We need to make our lectures a little more interactive because I have a feeling that uh, there are many students that I see here who are not responding. Sejal Mansoori, hello beta, how are you?
Yes, ma'am.
Are you following what we are doing in the class?
Yes, ma'am.
Good.
Okay,
Sadaf,
ma'am.
how do I pronounce your name, Sadaf? Is your mic working? Is your mic working, beta? Please unmute yourself. Okay. Okay. So are you following what we are doing in the class? Any problem? Good. Okay. So I am, what I'm going to be doing is that I think I'll start noting down the names of the people who are not responding back to me in the class. Okay. Because I need to monitor what is your output. In a traditional classroom settings, please see, it would have been a wonderful experience just by looking at you. Uh, Traditionally, your teacher generally comes to know how much you've understood and, whether we need to go forward, explain it more. But this is a different scenario. So that is why I wish to interact with you so that I know that all of you are on the same level. Okay. Okay. So, yeah, it is heartening to know that many people could do it themselves. Let us turn our attention back to the presentation. Okay. So you can see here that, see, what did you do? How did you derive the expressions for difference and borrow, students?
And by using K-map.
By
Yeah, ma'am.
using K-map.
Yes,
By
ma'am.
using
Right.
Kona.
Yes, ma'am.
Okay. But however, see that in this case, for example, in the case of borrow, now suppose this question comes to you, uh, and it carries a lot of marks, then you can obviously, you can draw the Carnot map to show that, you know, we're doing. But otherwise, in this case, when we look at this output borrow, you can see there is a single one, right? So
Yes, ma'am.
obviously, directly from the truth table, we are able to deduce that what this expression would be, it would be x dash y. That is another way to deduce it. That is what I'm telling you. Okay. Now, because there is a single one in the output column, so this is the most reduced expression, right? Similarly, in this case, you can see that we are having one in the min terms which are not groupable. Okay, which are not groupable, right? No group will be formed for these. This is 1 and 2 in a two variable Carnot map. They are diagonally placed, right?
Yes, ma'am.
Yes, ma'am.
Right. So they will
Yes,
not
ma'am.
be reduced any further, right? So that is why I could have deduced this as well directly from here. In your theory paper, you may still wish to draw the Carnot map, okay, for the sake of completeness. But otherwise, we could have seen it directly from here. So this is what this min term, for this min term, it will be x dash y, and for this it will be xy dash. So x dash y or xy dash, which we know is actually x XOR y. Is this clear?
Yes, ma'am.
Yes,
Are
ma'am.
we on the same
Yes, ma'am.
page?
Yes,
Yes,
ma'am.
students? Right.
Yes,
Yes,
ma'am.
ma'am.
So if you remember, what was the expression for sum of the half adder? It was again
X
x
or
XOR
Y,
y.
X or Y
It
or
was,
Z.
no. For half adder. For half
For
adder, it
XOR,
was,
This
XOR
was
Y.
full adder.
XOR
no,
Y.
half adder. Half adder I'm asking. So the the expression for sum output of the half adder was also x XOR y. Okay. And what was the expression for the carry output of the half adder? It
Ma'am,
was
X and Y.
xy, right? So the we find that the expression for difference is the same as the sum, and just in the borrow output we have replaced x by x dash, right?
Excuse me,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes,
Ma'am, in the difference expression that is written, ma'am, I think there is a mistake. They have written X
yes,
not expression.
yes, you're right. You're right. Here it should be, I'll just put it here, okay? I just correct it here. Yeah. It should be, please read it as x dash y or xy dash. Okay. So it should be this. Okay. Now can you read it correctly?
Yes, ma'am.
Right. So this is it for half adder. Okay. And now let us draw the circuit diagram. So you can see that this is more or less like a full adder only. Only in the borrow, I have to introduce a negator. Right?
Yes, ma'am.
Any problem up till now?
No, ma'am.
No, ma'am.
Right.
No,
Let
ma'am.
us let us turn our time and energies to the full subtractor now. Yeah. Nandini, can you please read?
Yes, ma'am. A full subtractor is a combinational circuit used to perform addition of three binary digits. Given the two input bits whose difference is to be calculated, namely the minuend and the subtrahend, and a third input which denotes a borrow over from the previous stage. The objective of a full subtractor is to generate two outputs, namely their difference and borrow.
So a full subtractor, like a full adder, basically deals with 3 bits of information. Okay. So with the full subtractor, we can actually subtract 3 bits together. Okay. This is the difference between the half subtractor and the full subtractor. Okay. The inputs this time are minuend and subtrahend as usual, and the third input we call as the borrow in. Okay. And what are the two outputs? The outputs are again the same, the difference and the borrow, which enables us to draw the block diagram of the full subtractor. Is this clear?
Yes,
Yes.
ma'am.
Yeah, Nandini, read on.
The truth table of a full subtractor can be drawn corresponding to the 2 raised to the power 3 binary combinations of the three input variables, minuend, subtrahend, and borrow, in x, y, z respectively, and their corresponding outputs difference and borrow out, d and b respectively, as illustrated in the figure.
So this input, the third input that we get here, we denote by borrow in, and this is the output, we denote it as borrow out. Okay. Yeah. So let us look at the truth table of the full subtractor now. Okay, so please see. Just give me a second. So you can see the truth table.
Yes, ma'am.
Yes, ma'am.
Okay, so please see how this is done. So this time we are going to subtract x minus, we're going to do x minus y, and then whatever is the intermediate result of x minus y, we will subtract z from that intermediate result. Okay, so in this case I'll do 0 minus 0, which gives me a 0, and
Zero.
this 0 that I've just got minus the 0 in the z column gives me a 0 again in the difference. And I did not need to borrow anything, right?
Yes, ma'am.
Any problem?
No, ma'am.
Let us look at the second row now. So 0 minus 0 is 0. Now this 0 minus 1, what do I do? As in the case of the half subtractor, I'll need to borrow a 1. So we put a 1 here. Yes.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Now this 0 that we got becomes 1
One.
0,
1-0.
which is
Yes, ma'am.
2. And 2 minus 1 gives me a difference of
One.
1.
any problem.
No,
No,
ma'am.
ma'am.
No, ma'am.
Let us look at the third row. Okay. So the first case is 0 minus 1. Okay. So what do I have to do? I have to take a borrow of
Borrow.
1, right? I take a borrow of 1, and then this becomes 1 0, meaning 2, minus 1 giving me a 1. Now this 1 minus 0 gives me a 1 again. Clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Any problem up till now?
No, ma'am.
No, ma'am.
Let us look at the fourth row.
No, ma'am.
Let us look at the fourth row. So 0 minus 1, as was the case in the previous row, 0 minus 1, we get a borrow. Okay, so that this becomes 2, minus 1 is equal to 1. Now this 1 minus the 1 in the z column gives me a 0 as the difference. Any problem?
No, ma'am.
No, ma'am.
No, ma'am.
No, ma'am.
Good. Let us look at the row number 5. So here 1 minus 0 is 1, right?
Yes, ma'am.
Minus, now this one minus 0 is again,
1.
and we did not have to borrow anything. Clear?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Next is 1 minus 0 is 1, minus 1
0.
gives
0.
the difference of 0, and we did not have to borrow anything. Next is 1 minus 1 is equal to 0,
Zero.
minus 0 is equal to,
Zero.
0.
Zero.
and we did not have to borrow anything, right?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Good. Next is 1 minus 1 is equal to
0.
0. This 0 minus 1, I have to take a
Again a
borrow.
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 So it will turn into 2 minus 1, which is 1.
1.
1.
Any problem?
No,
No,
ma'am.
ma'am.
No,
No,
ma'am.
ma'am.
Is the
No, ma'am.
truth table clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
1, right?
Ma'am, last row is not clear to me.
Okay, 1 minus 1 is 0.
Okay, ma'am.
That 0 that we've got as the intermediate result minus 1 in the Z column. I have to take a borrow.
Yes, ma'am.
So that 0 will become 1 0, meaning 2.
Yes, ma'am.
Minus this 1 gives me a difference of 1.
Okay, ma'am.
Okay,
Any
ma'am.
problem?
No, ma'am.
Ma'am.
So this seems like fun, student?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Good, good, good,
Yes, ma'am.
good.
Yes, ma'am.
Okay. So I'll again give you a minute to do the next step. That is to derive the expressions for difference and borrow. Okay.
Ma'am, I did it already. Is the difference the same as sum again? Like x, XOR y, XOR z?
It might be. I don't want to give a spoiler to everybody else. Let's wait and see what are their responses. Who was this, by
Okay,
the way?
ma'am. I'm Chenika.
Chainika. Okay, good Chainika. Let's see what other people get. Please work out, everybody.
Ma'am, I'm also getting that
Yes,
only.
ma'am. I'm also getting XOR, Y XOR Z.
Yes, ma'am.
Yes, ma'am. Same, ma'am.
Yes, ma'am.
Okay, good. Anyone else would like to try?
Yes, ma'am. Difference is X XOR Y XOR Z.
Okay, yes. So, yes, you can see let us look at the Carnot map for the difference. So this is the Carnot map. There is no grouping possible. And as we had done for the sum, if you remember, if we had done for the sum, this comes out to be the difference can be written like this, right? It can be written like this as the normal min terms. And then we had taken x dash common from the first two terms and x common from the last two terms. So that what I had was x dash into this is y XOR z. And what is this? This is
No,
y
that.
x nor z. You know what happens actually here is that sometimes some version of the word supports a particular symbol and the other one does not, right? I'll just give me a second, let me try. This should be x nor here. Okay, students, this should be x nor. Let me see if I can just insert that symbol. Let me know if you can see it before me. Can you see it, Beta? Can you see the X NOR symbol here somewhere?
Not yet, ma'am.
Right.
No, ma'am.
Ma'am, just give it a multiply sign for the time being.
Ma'am,
Yes,
it's
ma'am.
there in
Yes,
last
there
row.
it is.
On, ma'am.
Oh, I'm sorry. I was speaking while I got muted. Yeah. So this derivation is the same as the sum of the full adder that we had seen there. Just repeating it for your convenience. So this is x dash. This we know is this is same as y XOR z. This is x, and followed by this we know is y x nor z, right? So if we put a is equal to x and b is equal to y XOR z, then what my expression turns into is A XOR B, right? Putting back the values that we've just assumed, we get difference is equal to X XOR Y XOR Z. Does somebody have a problem in this?
No, ma'am.
No, ma'am.
No, ma'am.
No, ma'am.
Okay, good. Let us look at the borrow expression now. Can you please work out the borrow expression as well? And then
Yes,
we'll compare notes.
Yes, ma'am. I did
Ma'am,
it.
it is x
x
dash
dash
z.
z plus yz plus x dash y.
Yeah, ma'am, exactly.
Yes, ma'am. Same.
Yes, ma'am.
Yes,
Same.
same. Good. Yeah. Does somebody need a minute to work it out? So you can see here, this is the Carnot map. This is the Carnot map. Is this the Carnot map that you're getting?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Right. So these are the three groups that I can form. Three doublets, no quad possible. Okay. No octet possible. So this is the first doublet, second doublet, and the third doublet. So correspondingly, I get x dash y or yz or x dash z, right?
Yes, ma'am.
Yes, ma'am.
Yes. So again, you see that if I replace x by x dash, the expression is the same as the full adder, the carry of the full adder, if you remember,
Yes,
Yes,
ma'am.
ma'am.
right? Okay,
Yes, ma'am.
right. So we are going to draw this circuit diagram.
Excuse me,
So,
ma'am.
yes,
Ma'am, in this diagram, shouldn't there be three AND gates?
yeah, as we had drawn yesterday. Right. Now, there was a reason why we had seen this same diagram for the full adder also. You remember yesterday?
Yes, ma'am.
There is a reason. Okay. Why? The reason is that this expression of borrow and uh, of carry of the full subtractor can actually be also represented in uh, the using the XOR gate. Okay, so sometimes if you're not given three AND gates, or as we may see later, if we construct a full adder from two half adders, then what do we have with us? We have two XOR gates, right? A half adder means one XOR gate for the sum and one AND gate for the carry.
Carry.
Yes or no? Right.
Yes, ma'am.
So when I'm joining two half adders to form a full subtractor, what we do is we re-represent this expression in the forms of a XOR operation. Okay, so the expression remains the same, only that we do certain Boolean uh, operations on this using our Boolean postulates, and we re-represent this. Okay, so that we can use the existing output of the XOR gate that I am getting to get my output. Okay, so that we will have to see how to do. Okay, and then this diagram will become clear to you. Okay, but there is no stopping you. You can simply draw that diagram using 3 AND gates. Okay, just remember to replace x by x dash by putting a inverter out here. Is this clear?
Yes,
Is
ma'am.
this clear?
Yes, ma'am.
So what
Yes.
you see is an alternate representation. This is not wrong. This is an alternate, actually more commercially better commercially usable alternative to the full adder and the full subtractor circuit that we generally draw. Okay, but uh, it is not required. If you get a question to design a full subtractor, then you don't need to give this circuit diagram. Okay, you can simply draw your simple circuit diagram. That will fetch you full marks. Is this clear? So it is for a reason that I had, you know, included this figure here today to show you, because I wanted to explain yesterday you were too new to absorb this fact. Okay, and some people who would have just barely understood the concept would have got confused. Okay, so students, this is it for today. Is there any problem in today's class?
No, ma'am.
No,
No,
ma'am.
ma'am.
No,
No,
ma'am.
ma'am.
Excuse me, ma'am.
Yes.
Ma'am, that assignment that you sent us, we are still not able to access it.
I'll add the access rights. I'll give you the access rights, then you will be able to access. Okay, so I'll enable the access rights today. Okay, after this class I'll share the recording of this class with you, and I'll also enable the uh, access rights of that assignment. Okay, so it is not a very difficult assignment. uh, it is a multiple choice assignment, although it will require you to solve many Carnot maps and all, but it is not descriptive. So instead of giving you a descriptive assignment, I thought I'll give you a applied assignment so that you can practice the concepts that we have been doing in the class so far. Is this okay, students?
Yes, ma'am.
Yes.
I have
Yes,
also
ma'am.
included a time of 1.5 weeks, somewhere around that, for submission. But it will not take you that long. Okay, it should not take you that long. Only 2-3 days, maybe. That's also, if you don't sit at a single stretch, then it will take you this time, right? Uh, this assignment that I've given you this time, this assignment, the marks of this assignment will be included in the final assessment. Okay, so I request you to be uh, doubly sure before submitting this assignment. Please check your answers and then submit. Okay, although I have not made very difficult questions, but still. Is this clear?
Yes,
Yes,
ma'am.
Yes.
ma'am.
Yes, ma'am.
Yes, ma'am.
Now, before we break off for the day, I'd just like to, you know, uh, show you this broader picture of the combinational circuit. So these are the different types of combinational circuits that are generally seen in market. So the first category of the combinational circuit that are deployed are arithmetic and logical combinational circuit, which includes adders, subtractors, and then there are circuits which are known as adder subtractors. So a single circuit does both the things, that is a adder and the subtraction, and then the comparators. Okay.
Excuse me,
uh,
ma'am.
yes.
Ma'am, are you presenting the combination circuits in the screen because it's not visible?
Oh, I'm sorry. Okay, so I'll just change the screen then. In that case, thank you for letting me know. Can you see this picture now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Now it's feasible.
Okay, so you can see that there are three categories of the combinational circuit. So the first one is the arithmetic and the logical combinational circuits, which includes the adders and the subtractors. And then there is a different kind of electronic circuit that is known as an adder subtractor, which can do both the addition and the subtraction. And a fourth kind of circuit which falls in this category, namely a comparator, which is used to compare. Okay, but we are restricted only to adders and subtractors in your course. Okay, then data transmission, multiplexers, demultiplexers, encoders, and decoders. So we will be doing all these kinds of combinational circuits in the second chapter. Okay, and we will be also using these circuits widely. Clear? And then come the code converters. So binary, gray, BCD code converter, XS3 code converter. So these are the code converters which convert uh, numbers from one given code to another given code. Okay, for because as we have discussed, we use different kind of number systems or codes in our day-to-day language, in our day-to-day life, but computers work with binary. So these kind of code converter circuits are therefore required to do these conversions. Okay, but we are not required to see these code converters in detail. Okay, but you may get a question. Otherwise, you can get a question on combinational circuits uh, that tells you to design a combination circuit where any objective is given. So, for example, you may get a question in your theory exam which just tells you that design a combinational circuit which is capable of adding 3 bits of information. Okay, so the word full adder is not mentioned, or subtracting 3 bits of information, and the word full subtractor is not mentioned. Clear? Or any other problem is given. So we will be discussing more about that. I'll try to take a question or two of such problems, generic problems, and we'll try and design combination circuits for them too, maybe later. Okay, but you need to practice how to design the combinational circuits. Once now, see, we've done the design of combinational circuits in such details now, and I have very patiently, very slowly gone through each of the stages with you so that you feel confident in each of the stages of the design. I hope it is clear to you.
Yes,
Yes,
ma'am.
Yes,
ma'am.
yes, ma'am.
Yes, ma'am.
Okay, right, right, right.
Excuse me, ma'am.
Yes, Bete.
Ma'am, like I was just wondering that suppose we are given a question, or I just made it up myself, that if there were four inputs, suppose we have a adder in which there are four inputs, 4 bits of information. So
Hmm.
the steps will be just like this, like X, Y, Z, W, and sum and carry, just like
Exactly.
this.
Yes.
So we can just make a truth table and it will have 16 rows, and then we can find the outputs and accordingly make K-maps and then the circuit.
Yes. You are right.
Okay, okay.
Excuse me, ma'am.
Yes, Pita, tell me.
According to Chanika, she told that we would have 16 rows. But ma'am, we would have two borrows also, two borrow options.
Bete, what she's talking about is the input variables.
Ma'am,
Input
for
variables.
difference, I am telling. Ma'am, for difference, I am telling that if We would have four outputs.
Yes,
The
you will have
inputs.
two outputs. You will again have two outputs. One is the difference and one is the borrow. Okay, what she's saying is that if we want to subtract 4 bits, see, obviously, whenever we discuss a question like this, Chainika, you would
Yes.
like to understand whether such a thing is possible. You know, whether such a problem statement would make any sense in the uh, day-to-day life, whether it is going to be logical enough. Okay, so that
Okay.
is something that we may have to see. But what she wanted to ask was perhaps that is the same process going to work for any such kind of question? Am I right, Chainika?
Yes, ma'am.
Right. So that is what I have clarified to her, that yes, the same process would work. Is it
Excuse
clear?
me, ma'am.
Yes.
If we take the input, suppose 0 1 0 1, then 0 1 means then one borrow we need, then the 2, like this. And can you understand what I am telling?
No, not right now. You can send it to me. You can just write it down on a piece of paper and maybe, just
If
how to
suppose the
convey. You can
inputs
send
are
it.
zero
You
one
can send
zero
it on
one.
WhatsApp. You can
Okay,
just
ma'am.
write it down on a piece of paper and click a picture and send it to me on WhatsApp, and I'll reply there.
Okay,
Okay,
okay.
so that I
Okay.
can see what you are asking, right? Okay, so any other question? Yes,
No, ma'am.
Ma'am,
Ma'am, excuse me.
yes, tell me.
Ma'am, if there are four inputs, as Chanika said,